emergency. I didn't know you meant like a here emergency. I thought you meant like an IRL thing.
No, here.
Word.
Not firing. You don't know why.
Oh, good.
Oh.
There it goes. He just fired.
Yay! They'll try and tap the starter with a fucking screwdriver. That helps me a lot.
Okay, let me get my
Griffin.
Okay, my mouse back. Okay, I'm gonna introduce.
Wait, so how do you change your status again?
Okay, that'll be
Your status.
anyway.
Like,
All right, you ready, Mako?
Yeah, like the
how my
I'm ready. I'm ready.
Okay, if I can get everyone's attention, please. We are going to go ahead and start the stream, admittedly a few minutes late. Again, VR chat, perfectly balanced platform. So please be aware that the YouTube live stream is currently live. Today we are proud to present our very own Mako Fox़, who will be presenting on surviving extreme pressure and overview of barophysiology. Mako is an applied physicist working in mass spectrometry with a side passion in scuba diving. In the scuba world, he is an open water instructor and a rebreather technician. So please, Mako, take it away.
Hello, and welcome to an overview of barophysiology, or how pressure affects the body. I'm your host, Mako Fox़, a name loosely derived off of the Mako shark, but a lot of my in-person friends know me as Diver Otter thanks to my scuba career. I've been around DegenTech for about a year and a half now, and I'm really excited to finally be presenting for you guys. Outside of scuba, I have 2 bachelor's degrees in physics and applied mathematics. I'm working in mass spectrometry, and I've recently moved to Switzerland, where in the next few years I'm hoping to pursue graduate school. Hopefully something related to like space exploration or the upcoming moon landings. And I'd really love to present on this sometime soon, but my current work doesn't really let me get into the technical detail that I'd really like to on that topic. So instead today we're talking about my side career, my side passion of scuba diving. I have been into scuba diving all my life. Both my parents are avid scuba divers, so I grew up hearing all sorts of cool stories, watching cool videos. And I took scuba classes as soon as I could, and I just didn't stop. So sooner or later, I ended up teaching them. I worked my way up as a PADI dive master for about a year and a half, doing some assistant instructing. And then I moved on to an open water instructor for SSI for about 3.5 years. There I, taught classroom lectures, worked in the pool, did open water tests, and eventually worked my way up to do dive trips, kids summer camps, and it's a fair amount of underwater photography. On the side, I was also an equipment technician for Poseidon on open circuit and closed circuit rebreather. But I never really did that for customers. That was mostly just an interest of mine that I wanted to learn how that went. With my move, I'm taking a break from scuba these days, but I'm keeping up with freediving, which is really deep breath hold diving. Today, we're going to be looking at how pressure affects the human body and explain some of the science and technology behind pushing the limits of our human ability. Now, one of my favorite parts about DegenTech is getting to hear field experts come up here and get really in-depth on a very narrow topic. But that's not what we're doing today. I'm going to be trying to take us from zero to hero. So I'll even bring novices up if you don't know anything about scuba diving. Hopefully I can bring you along and at least give you the basic concepts of how these really advanced pressure physics work. For some of the more advanced technical topics that I don't have direct experience in, I was lucky enough to get in touch with and consult with a lot of different community members who have direct experience in these fields. And they have supplied me with way more information than I can share with you today. So it kind of ballooned. I'm going to be moving really fast, and I can't really get in detail on a lot of these things. But if you're a certified diver, or you're just keeping up with what I'm putting down, some of the blue text will have some further information. It'll have some citations, and so on. The main topics we're going to be covering today, we're going to start in some foundations in physics, just to make sure we're using the same terminology, you understand what I'm talking about. And then we're going to get our feet wet with recreational diving. That's like the entry-level scuba certification, and that's where most scuba divers stay within. But that'll give us a good introduction to a lot of the effects that we're going to be talking about. Then the main part of the lecture is going to be the advanced diving, the really advanced deep water physics, on how we deal with that. And then at the end, we're going to kind of go the other direction, take a break, go to low pressures, and see how these pressure effects apply when you go to space or very low pressures. Okay, so for the purposes of today, all we have to worry about for pressure is think about it as how much something is squeezed by the ambient fluid around it. So if you think about where you're sitting right now, all the way up to the edges of space, there's a bunch of air molecules that weigh something, and as gravity pulls it in around you, it squeezes around your body and provides 1 atmosphere of air pressure. That pressure can vary on altitude and a bunch of other things, but for simplicity, I'm just going to call that 1 atmosphere of sea level pressure. Between all the different things that I'm going to be talking about, it's going to change units a lot, but I don't really want us to focus on the numbers too much, so I've roughly translated it all just to atmospheres, just so you get a rough comparison idea of where each of these effects take place. The first thing we can see up here is that we have 1 atmosphere of air pressure at the surface, but because water is so much heavier and so much more dense, in only 10 meters of salt water, we've already added this whole 2nd atmosphere of pressure to the diver, and that's just going to continue as we go down deeper and deeper. Air is a compressible fluid. That means if you were to think of a balloon or some other squishy container, you can squeeze and compress the air inside of it. And the same thing is going to happen in the diver's body. As that pressure increases around a diver, the volume is going to decrease. It's going to get scrunched down. And more importantly, this goes both ways. So we see going from the surface down to about 10 meters there, we've already doubled the pressure, so the volume goes down by half, and vice versa. Coming back up 10 meters, it's going to double the volumes that we're dealing with. Diffusion is an important topic today. Basically put, it's just how particles spread out from a high to low concentration, and in our case, it's going to be going from a high pressure to a low pressure. It's important to note that this also happens between a gas-liquid barrier. So if you have a really high pressure gas above a liquid, it is going to diffuse. It's going to work its way into that liquid. And once again, vice versa, when you remove that gas pressure, that dissolved gas in the solution is going to need to come back out. This can be modeled as exponential decay. It's just random motion of the particles. And when you have a really high gradient, that moves a lot faster than when the gradients are similar. Partial pressure is a simple concept, but just an important term that I'm going to be using a lot here. So if we were to consider a mixed gas here with 3 equal parts, A, B, and C, if that's at 1 atmosphere of pressure, then we'd say that A, B, and C each have a 3rd partial pressure atmosphere for each of those gases. And that's going to be really important for us because the actual pressure effects I'm going to be talking about typically will depend on the partial pressure of an individual gas. I kind of think of this of like the sheer number of that one molecule that are present and causing all sorts of pressure effects. Here we see just an example of air. We go from 79% nitrogen, 21% oxygen, and we can split that into its component parts. Some basic cardiovascular biology. We breathe in, we take in oxygen into our bodies, we breathe out CO2, and this gas exchange happens at alveoli air sacs. These are little balloon-looking things at the end of your brachial tubes in your lungs, and these just create a much larger surface area for that diffusion to occur across. Once that occurs, then blood takes around 20 seconds, very roughly, to circulate around the body. But do note that the small capillaries and a lot of our body tissues will take a lot longer for that blood and the gas supply to work through the whole system. Okay, let's get started with some of the diving. This is recreational diving. This is most of the diving that we do for fun. We go out, see all sorts of cool things, and this is within the first 40 meters or 5 atmospheres of pressure. Barotrauma is the first topic we're going to talk about for this. And it's not only a really cool, fun game, but it's the actual medical term for pressure injury. And mechanically, this is very simple. This just occurs when gas gets trapped somewhere in your body, and it expands or contracts further than the tissue allows, which causes injury. And this can be really medically complex because it depends where that gas got trapped and where it's causing problems. For example, you can blow out an eardrum, collapse a lung, get air into your blood, and all sorts of really, really nasty things. And this is by far the most dangerous diving injury, but luckily this is also the easiest one to prevent. Simply by never holding your breath, ascending, descending slowly, and getting that scuba certification really mitigates this problem. And a lot of that entry-level scuba course is really revolving around making sure that you avoid this effect. But because this is so mechanically simple, this is really all the time I'm going to spend on this one. One more thing I'd like to point out, though, is that this effect is really exaggerated around the surface. If a diver is going to go from 40 meters to 30 meters, that's 5 atmospheres to 4 atmospheres, that's only 20% less pressure, so those volume spaces are only going to expand by 20%. while the same 10 meters from 10 meters to the surface, the pressure is now halved. So the volumes are going to double in size. So this gets really aggressive as you get right up towards the surface there. Decompression sickness is a much larger topic that we need to get into. And this is really going to drive a lot of the later complications that we're going to be getting into. We get a lot of complicated ways that we're trying to avoid this exact effect. So we want to make sure we're on the same page here. So when our bodies are under pressure, that compressed gas will diffuse from the high concentration around our bodies into the low concentration into our body tissues. And more importantly, on ascent, the opposite happens. The dissolved gas needs to come out of your tissues. The same exact thing happens in a soda bottle. If you think of a plastic soda bottle, you can squeeze it, it's really firm, it's under pressure, and when you open it, you relieve that pressure, and all that dissolved gas needs to come out and form bubbles. If you do that too aggressively, too quickly, all those bubbles coming out of solution form nucleation sites that allow a lot more gas to start coming out very rapidly, and you can get a runaway effect like soda fizzing over, and unfortunately the same thing can happen in the diver's body, so we really need to avoid that. Oxygen just gets metabolized by the cells, so we don't need to worry about that. But nitrogen, being an inert gas that doesn't interact with our cells, it needs to come back out through the bloodstream. And more formally put, decompression sickness occurs if that partial pressure of nitrogen becomes too great compared to the ambient. Surface tension, to some degree, does suppress bubble formation in the bloodstream and in the tissues, but this doesn't always work when that pressure gradient becomes too great. And it actually turns out that bubble formation is very common in scuba diving, and we call it silent bubbles because they typically don't cause symptoms. It turns out the size and the number of the coalesced bubbles are the primary driver of decompression sickness symptoms. And these symptoms can be really complex as well because, once again, it depends where these bubbles are collecting in the diver. For example, they can collect in nervous tissue, typically around the joints. This is where decompression sickness gets its other common name of the bends. As bubbles collect around the nervous tissue and suppress it, causes a lot of joint pain, and divers tend to curl their joints in that. These bubbles can also build up under the skin and cause a rash. They can block capillaries, which can lead to stroke-like symptoms or severe lung difficulties and problems. Or if they collect in the ears, they can cause vertigo and all sorts of disorientating effects, among many other possible symptoms. Typically, I'd say a diver with decompression sickness will get a rough smattering of different symptoms, but typically not all the symptoms. If a diver is experiencing decompression sickness, a lot of beginner divers would just naively think that you can put the injured diver back underwater, compress those bubbles. But once those bubbles have formed, it's actually really difficult to get rid of them again. Instead, you need to get the diver to the surface, to a doctor, and into a hyperbaric chamber here. Here, a doctor can be in the hyperbaric chamber with you while they bring you back down to pressure. They squeeze down the bubbles, but then they also have you breathe high-pressure oxygen, which really helps that nitrogen off gas a lot faster because it has a higher, diffusion rate off that. And I was lucky enough to have experienced all this. I had a dive partner get decompression sickness, and it was unlucky that this happened to him, and he missed a lot of diving, but lucky enough that he was totally fine, and I got to go sit in the chamber and talk to the doctors, and I learned a whole lot about this whole process. Ideally, though, we are not treating decompression sickness, we are preventing it, and that's where decompression theory comes in. So once again, that partial pressure of nitrogen cannot be too great compared to the ambient pressure, so we need to prevent that from happening. Body tissues will exchange that nitrogen in and out at different rates, so we model that using what are called compartments. So like, for an example, our blood will diffuse very quickly and circulate through, while some of our more extremity tissues and stuff will diffuse much slower. So we need to model that with different half-lives and different rates that they're going to diffuse this gas. Here's a dive example looking at how compartments change over a dive. So throughout the dive, the diver's body is going to take on nitrogen, and all the compartments are always trying to move towards the ambient pressure and equalize. So at the start of the dive, we see that the diver has just gone down under pressure. The ambient pressure is much higher than the nitrogen in their body, and as we move on in the dive, the fast compartments are taking on nitrogen faster than these slow compartments. And sometime later in the dive, we see this first compartment here has actually become saturated or it has equalized with the ambient pressure, while some of the slower compartments have barely even moved. And in the last one here, as the diver starts to ascend, suddenly the partial pressure of nitrogen in their body is higher than the ambient. So now all of these compartments are actually off-gassing. They're letting out nitrogen. And where this gets really complicated is at the same time we have the slower compartments still taking on more nitrogen. So we need to watch all of this at the same time. In recreational diving, though, we make this a little bit easier. We just use no decompression limits, meaning that for each depth, we set a maximum time that we can't stay longer from, ensuring that we can always go right back up to the surface without any ill effects from decompression sickness. This is really simple in that first example, but then as we go on repetitive dives and we're off-gassing nitrogen at different rates, and then we go back down underwater, this gets really complicated. So modern diving just uses dive computers to track all of this constantly. It's also important to note that this is just a theory. This is just a bunch of compartments in math. It doesn't actually know what's going on in the diver's body. So we always add a healthy safety margin on top of that to make sure that we're staying well away from that actual limit. Now, if we want to avoid decompression sickness, if we want to stay down longer, then the most obvious thing that we're going to do is we're going to remove some of that nitrogen. If we're not breathing in as much nitrogen, it's not going to build up in our tissues. And as we ascend, it's going to help us off-gas it faster if we're not breathing in so much more right on top of it. So nitrox is a nitrogen-oxygen blend where we simply just add in more oxygen on top, which more importantly displaces the nitrogen. An example dive at 24 meters, our maximum limit on regular air would be 30 minutes, but by going to 36% oxygen, we've almost doubled that time already. Now, this doesn't get us away scot-free though, because oxygen under high pressure actually starts to cause some new problems. And that would be oxygen toxicity of the central nervous system. And to avoid getting bad symptoms, we're going to need to make sure that we don't breathe too high of a partial pressure of oxygen. That's going to give us a maximum operating depth that we can breathe a given gas at. This is an acute effect. It happens relatively quickly, and it also alleviates very quickly as the diver starts to ascend. Symptoms will range from visual impairments and seizures and a whole bunch of neurological type symptoms. And these on their own aren't too dangerous, but when they happen to a diver at depth, obviously this can be life-threatening. The exact mechanism is still up for debate, but there has been some really cool advancements done here. I am not a biochemist. I can't tell you what the funny little letters mean up here, but a very high-level gist of what's going on is that the high oxidative stress of having a lot of extra oxygen in our cells leads to problems in the mitochondria. And as that happens, our body tries to put in some protective measures, which lead to all sorts of neurological type of overstimulation and bad synapse type of stuff. Turns out that oxygen isn't the only gas that's going to give us problems at high pressure, though. Even that nitrogen we're breathing is going to start to cause more and more problems as we go deeper and deeper. Nitrogen narcosis is what happens when we breathe nitrogen under too high of a partial pressure, and this is a narcotic, like drunk impaired effect. Euphoric, it's generally a good feeling, but once again, it's not safe when you're down really deep with very thin safety margins. You need to bring your A game down there. The exact mechanism is unknown, but we can deduce that nitrogen isn't chemically reacting with our cells. It's causing some other effect, and we're going to get into some more details on that in the more advanced section in a moment. Instead, let's just take a break here. Let's look at what we talked about so far, because I'm moving very fast. So for the world of recreational diving, here's what we have to worry about. We have to worry about changes in pressure, make sure that we do them slowly to avoid that barotrauma for air spaces contracting and expanding too quickly. If we dive for too deep or for too long, when we come back up, we risk decompression sickness, as that nitrogen needs to work its way back out of our bodies. We can mitigate the nitrogen intake by breathing nitrox, where we add more oxygen to reduce the nitrogen in the gas. And diving too deep will cause problems both with the oxygen and the nitrogen as they start to cause neurological effects to the diver. And I have been up here just spouting about terrible things that can happen to you while you're diving, but recreational diving is actually extremely safe. Only around 2 deaths per 100,000 dives. And out in the real world, I've seen a lot of divers that just don't take safety seriously. So any diver that actually takes the dive safety seriously and the dive training seriously, it's a really safe activity to be doing. We understand these problems very well. Okay. Okay, now let's dig in a little deeper. So revisiting that decompression theory, what if we just want to stay down longer? Well, decompression is only a problem when we come up. So as we stay down longer and longer, eventually we're going to need to make what are called decompression stops on the way up. This is where we can no longer go directly to the surface. We're going to come up part of the way and stop and let our bodies off-gas some of that nitrogen more slowly. M value is just the formal way that we say the maximum allower pressure difference between the ambient pressure and the nitrogen built up in our tissues before symptoms start to occur. So we see here ambient pressure, and then up here it's kind of a gradient, but we draw an arbitrary line here where we say symptoms are very likely to occur. And of course, we always add in a safety margin on top of that to make sure we stay well away from it. A ceiling is just what we call it when we enter decompression diving. We can no longer safely go directly to the surface. So instead, the ceiling is the shallowest depth that we can safely go to before risking decompression sickness symptoms. We really don't have time to get into gradient factors, unfortunately. This is just the complicated way that we handle those safety margins. They're going to be different at different depths. That M value I was talking about is different for each compartment. So the layered complexity here ramps up very quickly. Maybe we can talk about this after the lecture. Going back to that nitrogen narcosis, it turns out that nitrogen's not the only gas that causes this effect. And actually, most inert gases under enough pressure will cause narcotic effects, and it will affect the nervous system. Once again, we don't know the exact cause going on, but there's a very interesting correlation that we can draw from, which is the Meyer-Overton correlation. And the gist of what this correlation points out is that the narcotic potency of a gas is directly related to its solubility in lipids, or how easily it gets into the fats of our tissues and stuff. So we see down here at the bottom, gases that are really soluble in liquids only are going to take a very low concentration before they start to give us narcotic effects. You might be familiar with this narcotic effect if you've ever gotten nitrous or laughing gas at the doctor's. That's right in the middle there. And as we go towards the really lipid-soluble gases, other recognizable anesthetics would be like ether, chloroform, stuff like that. But we're much more interested in going the other direction. As we go to higher pressures, we see that nitrogen actually starts to become narcotic. And if we want to avoid that effect, then we can jump right to the end there, where we see helium is going to be the ideal gas to avoid these narcotic effects. There we go. So, to deal with all this, we start using more complicated mixed gases. We already talked about nitrox. That's just a nitrogen-oxygen blend. And by breathing less nitrogen, we can help accelerate that nitrogen off-gassing. We take on less nitrogen, and decompression sickness is less of a concern at that point. However, it does have that maximum operating depth of oxygen, so it can only take us so deep. Ideally, what we want to be breathing then is heliox, where we replace that nitrogen with helium. And while helium does still have decompression considerations, because it is such a lightweight gas, it moves in and out of our tissues much more quickly, and it's far less of a concern. However, most divers actually avoid pure heliox because helium is pretty expensive. I believe a full cylinder of it can range between $100 to $200, and as you're going deeper and deeper, you're using a lot of cylinders at one time. So instead, a lot of divers will use trimix for deep diving. This is a blend of helium, oxygen, and nitrogen together. This can be tailored to the specific depth, where you breathe as much oxygen as you can safely breathe before oxygen toxicity becomes a concern. And then you lower that nitrogen so that you don't have to worry about long decompression stops on the way up. And then the rest is that helium that can offset all those other effects. Not a gas mix, but a different class of gases are hypoxic gas. As we're pushing even deeper underwater, before long, the regular 21% oxygen in our air under that high pressure starts to become toxic. At this point, you need a gas blend that has less than 21% oxygen in it in order to breathe it safely at depth. And this adds more complication because now you have to worry about a gas that's no longer safe to breathe shallow or at the surface, and while all your other gases aren't safe to breathe at depth. So it becomes a little complicated as you need to make sure you're breathing the right cylinder at the right depth at the right time, and you're tracking it all carefully. So as this gets more and more complicated, you have to deal with more and more cylinders. Another effect is as you go into higher and higher pressure, you're actually breathing in more air molecules. You're pulling the pressure out of that cylinder faster. So, for example, as you go from the surface down to 4 atmospheres of pressure, it's like taking 4 breaths of air per single breath. And that just goes further and further as you go deeper. So before long, you're just lugging way too many cylinders, so it's no longer practical to do it this way. And at the same time, we're breathing in this oxygen at 21% on the surface, and then we breathe out 16%. We're actually not collecting a lot of the oxygen that's in the gas we breathe. So we need a better way, and the better way is closed circuit rebreathers. Open circuit is traditional scuba diving where you breathe in and then you breathe out a bunch of bubbles. It's just open, it goes away, you lose the gas. Closed circuit rebreathers will recycle that breath in and out. So you trade the air between the diver's lungs and then two counter lungs in the system that kind of hold and store the air. The system then replenishes the oxygen that the diver used, and it scrubs out the CO2 using like a soda lime scrubber that chemically sticks the CO2 and catches it. So that way it can constantly be updated. This is the most simplistic view of a rebreather we can get. Just simply add oxygen, remove CO2. But as mentioned, oxygen toxicity is a concern, so this isn't really viable at depth. Instead, we're going to need to add what's called a diluent. In this case, we add in an extra gas. Typically, this is going to be your bottom breathing gas, the deepest gas that you're going to want to use. And then for the rest of the dive, when it's not at an optimal oxygen percentage, you're constantly adding in more oxygen and managing that with a computer. So the simplest components here are just adding in oxygen, adding in some diluent when you need it, and scrubbing out the CO2. The real complication of these things comes in from introducing gases in a really reliable way, monitoring the oxygen partial pressure, and managing that all with a computer and making sure you're tracking it all throughout the dive. So that's really where the complication comes in. But these systems can start to get you really deep. The other benefit of this is that it can constantly optimize your oxygen percentage. And this helps with that decompression, gives you shorter times, and you're not stuck with any one blend. You're getting the perfect blend at any depth. However, as you push this system even deeper and deeper and deeper still, physical exertion starts to become a concern. As you're breathing in, say, 10, 20 breaths of air per single breath now, air becomes pretty thick. And this can become a concern as you're having to push it through a loop, through a CO2 scrubber. This can actually be a lot of exertion to start working. So that is a concern at extreme depths. Of course, this is a really complicated system to trust your life to. So divers use a bailout system, which is a fully redundant way to get back up to the surface, do all the required decompression times and stuff like that on a totally backup system. Gavin, the Border Collie, and Dave Rab were nice enough to help me out and give me some pointers on this section here, and they gave me a bailout closed-circuit rebreather dive plan. So they gave me a plan of what would happen if they were diving on a closed-circuit rebreather at depth, and at the worst possible time it failed, and they had to plan out what bailout gases to use to get to the surface. So basically what's going on in this plot is we see the diver goes down to depth, 160 feet, and hangs out. This is a decompression dive, so immediately we see a ceiling coming down here. The diver can no longer go directly to the surface. They have to stay below that line in order to avoid decompression sickness. Since this is a closed-circuit rebreather, on this partial pressure of oxygen plot, we can see the rebreather is constantly maintaining the optimal partial pressure of oxygen. And then 20 minutes in right here, we see the rebreather has failed, and the diver needs to go to an open circuit now and figure out how to get up to the surface. We can see the partial pressure of oxygen shift as they start to ascend to a lower pressure. And once they get to their decompression stops up here, they can switch to a really high oxygen percentage nitrox to really optimize and speed up their decompression time so they don't have to spend as long there. Other thing to notice here, these are just the pressures in the cylinders for the different gases. That's something you really need to plan out for. Make sure that each stop and each gas that you need for specific depths, make sure it's going to last you long enough to get you back up to the surface. Commercial diving is the next step. This is more industrial style work. We've now left the world of scuba diving, of self-contained underwater breathing apparatus, and now you have a whole industry and company behind you funding this type of hardware and this type of work. Typically they dive what's called hard hats, so they have a big heavy helmet. They get air supplied from the surface or from some sort of supply rig, and that's pumping air down to them so that they can do underwater welding, shipyard work. Though most commercial divers don't work in deep sea, they typically are doing that type of work, or they're doing freshwater, water treatment plants. And I've heard my fair share of these divers having to dive in like raw sewage and all sorts of horrible simple things. So while these divers get paid a ton of money, I have yet to meet one who says it's worth it. Besides that, though, when these divers start diving really deep, this is what we call saturation diving. So these are like oil rig type of workers that need to go down to the bottom of the ocean and do heavy industrial work for long periods of time. And at this point, decompression stops and waiting to come back up to the surface just becomes really impractical. So instead, they just don't decompress. They take their whole month-long shift at pressure, and then at the end of their month-long shift, it takes them 4 to 8 days to slowly decompress back out of that environment. They don't just live at the bottom of the ocean, though. They live in a hyperbaric chamber, usually on a ship or like an oil rig or something like that, that they have a safer space to stay in, de-stress a little bit, and when they're ready for work, then they board what's called a diving bell, which keeps them at this really high pressure and drops them down to the ocean floor at the pressure that they're already acclimated to. While we've negated the decompression symptoms, we still have to worry about nitrogen narcosis and some other high-pressure gas effects. And this is where we start to reach the real physical limit of breathing gas underwater, and this is high-pressure nervous syndrome. At this point, it's not the helium causing the problem, it's the high pressure itself around the body starts to cause problems with the nervous system. This can be a lot of different symptoms, as we see over on the right, but typically they're related to like motor control problems, like twitching, stuff like that, starting around 150 meters, but then it becomes just debilitating over 300 meters, and this becomes a major problem. Once again, the exact mechanism's unknown, but we do have some strong leads and ideas of what effects might be contributing to the overall symptoms that we see. However, there is hope to push a little bit deeper than this, and that was when it was discovered that a little bit of narcosis actually improves this high-pressure nervous syndrome, and they seem to kind of counteract each other to some extent. That has led to some of the most exotic breathing gases in underwater pressure physics. What we're going to be focusing on is hydreliox. And this is where you mix in hydrogen, helium, and oxygen together. Because once we see up here, hydrogen is a very lightweight gas that has slight narcotic effects, not nearly as potent as nitrogen, which makes it ideal for this purpose. Where now, as a diver starts to get high-pressure nervous syndrome symptoms, they can then counteract that with narcotic symptoms and kind of like ride that knife edge down to very, very high pressures. I know you're probably thinking about like a Hindenburg situation, which is absolutely a concern. And above 4% oxygen, hydrogen can become explosive in these cylinders. So you need to stay below that, which means this must be an extremely hypoxic mix. It can only be breathed at extreme depth. This has only been used a few times in the world of diving, mostly in some Comex dives. Comex is a French dive research company that was experimenting with this around the 70s or 80s or so, and they made a few real dives using hydreliox. The deepest open water dive, meaning out on a real dive site, was to 534 meters, and the highest pressure a human's ever been in is 701 meters, where they just stayed in the chamber for research. And to get to that point, it took 15 days of slowly going down to that compression, and then 23 days to slowly come back out of it. After these sorts of experiments, research into this really stagnated as robotics stepped in and was able to do this deep sea work safer and cheaper. However, we do have one notable example very recently where we had the first use of hydreliox in scuba diving in 2020. A team in New Zealand is diving a really deep cave, and they're starting to run into those high-pressure nervous syndrome type of symptoms, and they are experimenting with some hydreliox on how to deal with that. There's a fantastic YouTube video that goes into all their like wild testing that they do. I can link that later. But that's gonna wrap up the main section of advanced diving. So just a quick recap of what I went over here. Mixed gases. You need to balance the pros and cons of oxygen, nitrogen, helium, and in rare cases, hydrogen. Rebreathers are used when we go down deeper to make sure we can conserve gas and optimize that oxygen usage. Saturation diving is when the diver just stays down under pressure. We negate that decompression problem, and then we just deal with it later by slowly bringing them back up. And then the very extreme limits that humans have reached is using hydreliox, where they push past the limit of high-pressure nervous syndrome to use that narcosis to like ride that line, go deeper and deeper and deeper. And that was a lot. That was very fast. So I want us just to take a quick moment and step back. Here's my buddy in a luchador mask diving a shipwreck, and remember that scuba diving is for fun, right? Like, I love the technology, I love the theory of it, but we do this to see this incredible alien world that we live on, have a great time with friends on a beach, and just experience this very foreign place that we don't always get to spend time in. And it's great when you can make fun of your dive buddy using creative or offensive hand gestures, and when that doesn't get the point across, you can just point at them with a boy kisser, and that seems to get the message across. All right, let's go the other direction here. Let's go into space and see what low pressure effects do to the body. The most obvious one is the Armstrong limit. That's the limit where blood starts to boil. But as we'll see, the human body needs quite a bit more pressure than that to actually survive. But that is the bare minimum to keep yourself from just evaporating away into space. We do want to optimize this, though. We don't want to just take a ton of pressure with us, because mass on spacecraft are obviously very important. All the structural engineering that has to go around it can really contribute to more weight. Some of the pressure effects we do have to worry about, however, we have to worry about those minimum pressures, make sure that we're getting enough pressure to survive. We still would have to worry about barotrauma, though this isn't really that common. It's only going to happen if you go through an extreme pressure change very quickly. Here's like a weather balloon, so we still do have to deal with this effect. And then in some cases, we do still have to worry about decompression sickness. If you're going from a high pressure environment where you're breathing nitrogen or other inert gases to a low pressure environment, you still absolutely have to worry about this. And for example, down at the bottom here, we see astronauts who are staying on the ISS at 1 atmosphere of regular air pressure, a bunch of nitrogen in their bodies. As they get ready to go into a low pressure EVA suit to go out on a spacewalk, they actually need to spend a number of hours pre-breathing oxygen or nitrox to slowly off-gas all that nitrogen from their system before they go out. Oxygen's going to be our main concern and our real bare minimum of what we can take. Pure oxygen, when we breathe out, the bare minimum we can get away with is about 1/4 of an atmosphere. That's because at the surface we're breathing 0.21 atmospheres of pressure, but as we go down to lower and lower pressures, diffusion isn't really a great analogy to what's actually going on. There is some more chemistry and other physics going on here, so we actually need a little bit higher partial pressure in order to get a good gas exchange of O2 in, CO2 out. Some other longer term effects that we have to worry about are atelectasis, which is where alveoli can actually collapse. Without nitrogen in here to prevent this, your blood can actually suck out all the oxygen and squeeze it shut, which can cause problems as you try to breathe in and reopen that space. Another long-term effect would be pulmonary oxygen toxicity, which is just really high oxidative stress to your body as you breathe pure oxygen environments for a long period of time. So instead, the best atmosphere, according to NASA, currently looking at going to the moon for the Artemis missions, you need that minimum of 0.25 atmospheres of oxygen, but you can only do that for about a day or so max. Really, it's only for EVAs. For long-term habitation, you need a little bit of that diluent in order to prevent those negative oxygen effects I mentioned. So that gives us a minimum possible long-term pressure of 0.35 atmospheres. As you might imagine, flammability is a concern. You might be thinking of the Apollo 1 fire that killed their astronauts on the ground in a bad test. But this is much more of a concern on the ground. Once you get into space, the lower pressure cabins will help a little bit, help make it a little less flammable. But more importantly, the convection goes away without gravity. So on Earth, we have convection and buoyant forces driving more oxygen into the fuel source, which feeds flames. While in zero gravity, we don't have that effect. So this is a concern, but it is less of a concern. Quick little bit on spacesuits. I got to talk to Peter in the DegenTech server. He's just a great person to talk to about this stuff. He builds spacesuits. I don't have time to get into too much detail, but I wanted to just share a bit about what I learned because I love this stuff. So what these suits need to do is they need to maintain that minimum pressure of about 1/4 of an atmosphere of oxygen and still allow the astronaut to move around in the vacuum of space. So the two main components of a spacesuit are going to be some sort of fabric or bladder to hold the gas in, and then you need a separate system to actually hold back the pressure. So if you think of a spacesuit like a balloon, it's just going to puff up and the astronaut can't bend a joint or move at all. And typically what they use are like straps or cables to physically squeeze the suit back together, provide some give in the fabric so that joints can move. We don't have time to get into this too much, but I just wanted to point out some fun things. For the Apollo EVA suits, the cool look is actually just the exterior pressure suit. Inside, this is the actual pressure layer. We can see all these different cables and stuff squeezing the astronaut together, and it looks considerably less cool. And I love pointing out this guy. One of the major straps on a spacesuit is going to be holding the torso from stretching out to be too tall, which is exactly what happened to this guy here. There's a lot of space above his head, and his chin's like right in the neck seal there, and he really doesn't look too happy about it. The personal life support system is basically like a rebreather for the astronauts. These are like the big backpacks that you see the moon astronauts wearing. This is actually, the gas loop side of it is actually very simple compared to the scuba rebreathers, because in this case you only have to worry about oxygen in the loop and just making sure that the system has enough pressure, and you're guaranteed the astronaut is breathing enough oxygen at that point. Still got to scrub out the CO2, monitor everything, but a lot of the complexity comes from making sure this is redundant and a life, supporting system, and then there's a lot of thermal regulation systems that they have to worry about in space. Tying it all together, there's one really strange, unique place in the world called NASA's Neutral Buoyancy Laboratory. And this is where astronauts go underwater and diving to train like they're on an EVA in zero gravity. And I really am excited to share about this stuff that I learned here, because I have an old coworker who actually was a safety diver at the Neutral Buoyancy Laboratory, and she was able to fill me in on a bunch of really fun, cool details, most of which I don't have time to share, but she did get to teach me a bit about the environmental control system that they use there and how they merged scuba diving and spacewalks together. So the goal of the Neutral Buoyancy Laboratory is to give these astronauts the best possible simulation of space that they can give. So they're going to try to remove all those diving considerations I've talked about and take care of that in the background, so the astronaut doesn't have to really worry about anything. So the pool is 12 meters deep. The suit's overpressurized a little bit. This simulates the pressure difference between the suit and the vacuum of space when it's actually in space. So this gives them a little bit of a higher pressure equivalent, like they're diving a little deeper. So they've mixed things, blend things just right to use 46% nitrox. This avoids the oxygen toxicity effects. It's not deep enough for that. But they've also removed enough nitrogen that these astronauts can train many, many hours. They can basically stay down indefinitely and still come back up to the surface without having to worry about those decompression sickness symptoms I talked about. Okay, wrapping it all up now. Just a few things going over what I talked about in space. Oxygen's key, and that's going to provide the minimums that we can survive with. We need at least 1/4 of an atmosphere to maintain normal, body chemistry, oxygen percentages. But we also need a little bit of diluent for the long-term habitation to avoid some long-term oxygen toxicity effects. This gives us a minimum habitation pressure of 0.35 atmospheres, and this is what we're going to be using going towards the moon for Artemis. This lower pressure really optimizes, the long-term effects with still being able to go out on EVAs very quickly without having to worry about long decompression times for the astronauts. Big thanks to the people who helped me with the more technical parts of this. Gavin the Border Collie and Dave Rab host a Telegram dive group. If you'd like to get more information on that, let me know. I can get you connected. Peter is in the DegenTech community. He's just an incredible walking space encyclopedia. He's making homemade spacesuits, and he's doing some really incredible things. So if you get a chance to talk to him, he's awesome. He's always in the Discord. Then a few other anonymous friends helped me as well. Citations, I don't know where these will be posted yet exactly. I think we'll put them in a new channel on the Discord. But if you're really interested in learning about all these papers that I researched and stuff like that, feel free to just reach out to me as well. I can send you the full citation list. Thank you so much.
Clap, 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 clap.
Great presentation. Thank you very much. Does anyone have any questions?
Hey, thanks again for the presentation. So I remember you saying that nitrogen was not the only gas that we had to worry about when it comes to decompression. But then in the NASA pool thing, you also mentioned that they reduced nitrogen so much that decompression is not an issue. What about the other gases, that scenario?
Yeah, that's a good question. So for the neutral buoyancy lab specifically, they're only using nitrox, so that gas blend is only nitrogen and oxygen. So those are the two gases they have to worry about. We have to worry about other gases, decompression in like heliox, trimix, stuff like that. Then we have to worry about helium decompression times.
Gotcha. Thank you.
Howdy, excellent presentation. I had a question, but then you just mentioned that they use heliox in the neutral buoyancy pool.
No.
Oh, okay.
No, they don't have to worry about it because they don't use heliox.
Oh, okay. I was about to say, I wonder if that would make their voices really squeaky.
Yes, it does.
Have you used any of these exotic mixtures beyond nitrox?
No, unfortunately, growing up in Colorado, there's not a huge tech diving community. I worked alongside a lot of my coworkers at the dive shop who are tech instructors, learned a lot of cool stuff. But this is more future looking for me, and a lot of the more technical sides of that section was inspired and helped out a bunch by some of the collaborators I had for this.
Cool. Any more questions? If not, I was going to ask, you had said you had some interesting stories from your friend who was a safety diver in that buoyancy pool.
Yes. Yeah, I got to sit down and really talk with her about some stuff. Yeah, I'm happy to get more in depth after the lecture as well, but I think some of the favorite things I got to hear about are that the safety divers actually train. I forget how often she said they do it, but they actually train in the suits. When they're training how to assist injured astronauts or astronauts having problems, they'll put one of the safety divers into a spacesuit and they'll pretend to have problems. So she's actually got to try it a number of times, see what it's like for them and know how to better assist them. Another really interesting point about the neutral buoyancy laboratory is that they spend a lot of time and effort getting the trim of the astronauts just right. Trim is where you're going to like sit in the water, and in space you can float just as well horizontally as you can vertically. But if you're in the water, you're tending to want to just bob in like a one orientation. So they spend a lot of time trimming out the weights and the buoyancies to make sure that these astronauts can flip and roll around, and they are making the movements, and the suit isn't like pulling them around any weird directions.
Oh, that's interesting. I also like the slide you had where was the gas lipid solubility. One of those on there is carbon or it's carbon tetrafluoride. I'm sorry, not carbon tetrachloride. Yeah,
carbon
I forget
tetrafluoride.
which one of those, but I think carbon tetrafluoride gives you like super liver cancer, like super fast. So it's just funny to see that on
these gases.
Yeah, it's like they probably tested that back in the 50s and like, oh, dude, this stuff rules. And then like, here we are, we're like, never breathe that stuff. It's banned everywhere. But, yeah. Anyone else got some questions?
Hey, can you please flip back to the slide with that mostly helium mix in the tank?
Hydrogen or helium?
I'm also just saying. Like,
Sorry, hydrogen. Yeah.
You know, like
Yes.
asbestos and
Here you go.
Yeah. How the hell do people breathe hydrox if there's barely any nitrogen and oxygen in it?
Yeah. So this is that extremely hypoxic mix I was talking about. So yes, this is something you absolutely cannot breathe at the surface. This would be deadly. But once we go under really high pressures, what really matters for our body is the partial pressure of that oxygen, not the percentage of the oxygen in the mix. So as you go down, that 4% oxygen here actually becomes really great. That's going to be over 1 atmosphere of partial pressure oxygen. That can become like breathing even more oxygen than a full oxygen cylinder at the surface. But yes, you absolutely cannot breathe that at the surface. That would definitely kill you.
One question. I think Is that gonna... No. That's gonna fucking not work.
Uh-oh.
Oh,
He died.
it's okay. I get water. Anyone want to jump in?
I'm guessing the death would be pretty instant with Hydrox if you breathe that on the surface.
Yeah, I mean, it would be like one of those really hypoxic events. I don't know if you've seen those videos of like people in a high altitude chamber where suddenly it's like, oh, the cabin of your plane just dropped out or whatever. It'd be a similar effect where like you just within seconds start to lose any conscious ability. You don't die right away, but you lose consciousness within, like 10 seconds or something like that. So yeah, don't mess that up. Don't breathe the wrong cylinder. Gotta be careful.
He's doing his yoga position.
He's so zen.
So, I know this is not really part of the presentation, but in terms of heat management, because like the water gets really, really cold, and how is it that the diving suits are able to retain so much heat that it doesn't become a problem while being so thin?
Yeah, that is a major concern, especially as you start going to extreme depths. There's a lot of strategies for it. Typically use. Was I muted the whole time?
No, you are
You're
fine.
Okay. Typically we use wetsuits, which traps warm water around the body. That helps keep you warm. As you go really deep or really cold, you start to use dry suits, which traps a full layer of air around you, and then you can dress up warmer underneath, stuff like that. It gets even more advanced as you go deeper, like commercial divers and the full rigs and stuff. They'll typically have like water vests that can pump warm water around. And just like in this dive here, when they were diving really deep into this cave, temperature problems were actually one of the main concerns that they're dealing with. And as they're going down, they have a bunch of safe spaces. Going down and coming back up, they have little pockets where they've heated up the water so that they can sit, warm up, recuperate a little bit. And another problem that these guys actually had is that hydrogen pulls away heat, conducts heat away from the body when you're breathing it much faster than nitrogen or these other gases do. So it really adds to that temperature concern as you breathe hydreliox.
Gotcha. What about the face? Because there's nothing covering the face.
Yeah, I mean, you can do the best you can do. You get a hood. You can do full face mask diving. So instead of just a regulator or a rebreather tube around your mouth, you can put a whole face mask on. But typically it's just, not enough is really exposed to the cold water. It's not that cold. Typically it's not a problem. But there are solutions to that. And when you're diving really extreme depths, like in commercial diving, you are once again going to have a full helmet on. You're fully protected from that deep sea environment.
Okay, let's carefully try this again. Sorry, you implied it before, but I wanted to know, how much oxygen do we not take on at a regular atmosphere, and then how much what does that curve look like as you go down deeper and deeper in terms of
Yeah. So here's just where I was looking at. This is what we do on the surface. We take 21% oxygen in, and then we breathe out 16% oxygen. So we've only used 5%. I don't know. That's a great question. I don't know the difference as you go down and breathe a really high partial pressure of oxygen, what that does. But obviously when you're breathing vastly different percent grades of of a hypoxic gas or something like that, that's really going to also play into, how fast you're breathing down that percentage. So the percentage is really relative. I believe the actual metabolism of O2 is pretty much the same.
I think I have a tiny question. I mean, I think there might be problems with visibility. For example, when you're going deeper and deeper, it will become moody, foggy, or something like that. Are there like any special devices which can actually allow you to see besides just besides the lighting?
That is a great question. That'd be great if it exists, but no. As it gets murkier and murkier, and you start to get sediments and stuff into the water, it gets obviously really hard to see, and a light doesn't help you, because if you turn on a bright flashlight, it's like snow and headlights, if you've ever seen that. It just blinds you, because suddenly all this light right in front of your face is reflecting back. So no, there's not a good way around it. If you're diving, like a commercial diver in a really low visibility, water tank or whatever, it's just zero visibility. And I've seen this on the bottom of a reservoir many times, and what zero visibility means, it's not just like, oh, I can't see. It's so silty in the water that it's just pitch black. It's like there's a hood over your head. You can't see anything because it's blocking out all the light. And that is scary and dangerous for sure.
Even like there are no special drones just to like make it dive a little bit further than what you see, right?
I mean, you can absolutely send in ROVs, like remote vehicles, to go explore ahead, and that's mostly how any commercial work is done these days, is using ROVs. But obviously, they're going to have a camera too. You can maybe get away with some like I don't know, like sonar type of stuff. I'm not really sure where that technology lands, but not in scuba.
Or like a really long, rod or something like that. Yeah.
A big stick.
Absolutely. The trusty stick poke.
Okay,
yes.
Thank you.
I have used that.
Guess.
I have used that.
All right, I got some questions in relation to the closed circuit breathing. If you could go back to the graph that has the oxygen, the diluent. Okay, so what exactly does the diluent do? I was not aware of this. All I was aware of was the oxygen part and the rebreather part.
Yes, so simply put, if we are breathing this oxygen under pressure, obviously it would give us oxygen toxicity. We have to have a way to lower that percentage of, or that partial pressure of oxygen in the diving loop. So that's what the diluent is for. Ideally, the way I like to think of it is the diluent is the actual gas that you're breathing throughout the dive. It's just like you took a bottle of Trimix down with you, but instead of just breathing all that out, you're constantly topping up that little bit of oxygen that your body's using. Does that make sense? I mean, I can go really in depth on this.
Kind of. So let's say you have goodness. How would you measure the oxygen that enters in your body in a closed circuit?
Yeah, so that is done typically by using 3 separate oxygen sensors. And these, I forget exactly how it works. It's like a cathode or something. It's measuring the actual percentage of oxygen in the gas you're breathing and then voting out a bad sensor if it exists. And this all is really important to go to the computer, because your computer needs to know the exact composition of gas that you're breathing in at that specific depth at all times. So yeah, it's gonna take in the oxygen, account for that. It's gonna know how much nitrogen or helium you're taking on at that moment, and it gets really complicated in that regard.
Okay. I noticed there's no sensor near where it gets to the little past the 14. There's no sensor there. Couldn't that be like a safety concern if for some whatever reason something happens with the diluent, and there's no way to really check what's actually entering the person's mouth?
Yeah, but that'd be a really hard issue, and I mean, this is really only one breath or so of gas. There's not a lot of air that's in this loop at any time. It's going back and forth. So yeah, you could. I feel like if you were to introduce so much diluent into the system that it becomes hypoxic, you would notice very quickly that something catastrophic just happened. It's to get down to a hypoxic level, you're trying to ride the line of 1.3 or so partial pressure of oxygen. So you'd have to lose a lot of that for it to become hypoxic, or you'd have to have a massive, much more dangerously would be if you boosted way too much oxygen in. We want to see that because too much oxygen will very quickly cause the CNS symptoms.
and this is perfect. It leads up to my next question. There was an incident where someone was, I probably forgot what like hellhole this man was diving down, but he was there to like recover like a body of another technical diver. And one of the mistakes that he made was he put he put too much on his little like rebreather console on his chest here. He put too much oxygen in his system. How did he not catch that? Like because there's like a system, right? You see the little computer with the oxygen center and it goes to his little like thing on the wrist. How do you not catch that?
Yeah, I mean that's tough. I don't know the exact scenario, but one of these valves going on over here is actually a manual override where you can just add oxygen back into the loop manually and you can ignore the automated computer. So maybe he was fucking with that for some reason, caused problems. It's tough to say. Your computer would be screaming at you very quickly, but it will allow you to do whatever you need to do. I would say most likely it's like narcotic effects going on at that point or some sort of incapacitation of their logical reasoning.
Yeah, he overexerted himself, and he was confused while like he was wrapped up in like the net he was trying to grab for the body, which is unfortunate, but it is what it is.
Yeah, and that's where that physical exertion becomes a major concern at depth. As you're working really hard, you're breathing harder, you're having to really push a lot of air in and out, and CO2 exchange actually becomes a major problem as well, where you just can't off-gas the CO2 very well, and it starts to give that burning need to breathe effect, and that just very quickly turns into a life-threatening scenario.
Yeah. With open water, though, you can just drop weights and just shoot back up.
Watch out for barotrauma, but yes.
I mean, hey, at least your blood won't boil alive.
Yeah, recreational diving avoids a lot of the worst of these horrible things that could happen to you.
Yeah. Drop weights and just shoot back up. All right, that's it. Thank you.
Like a rocket ship.
Two more questions if you have the time. First, you mentioned that commercial diving doesn't really go to really high depths anymore or really low depths anymore because we use robots instead, right? What scenarios do we still use commercial divers to go to depths that normally would be done by robots?
Yeah, so to elaborate a little more on that, I actually looked into the numbers. It's around 10% of commercial divers actually do the deep saturation diving, so it's not very many. I wish I could give you like specific examples, but it's almost always regarding like oil rigs. So they're setting up a well or working on pipelines and stuff like that. I was able to talk to a commercial diver for this lecture, but he does not do saturation diving, so I couldn't really get that specific with what it's like to actually work down that deep. But typically welding, moving bolts, directing robotic and like crane equipment.
Gotcha. Thank you on that. The second question is, I read somewhere that like on the International Space Station, on a place like that, they will use like carbon to scrub air that has already breathed, and then they'll just top it off with oxygen, right? How efficient is that, and like is that viable for diving?
That's a good question. So yeah, that's actually what's pictured here. This is one of the many life support systems on the International Space Station that's going to recycle that CO2. It's going to replenish the oxygen. I can't say off the top of my head how efficient that is, but they are, constantly improving it, and they're up to a really high efficiency so that they recycle all their water, their gas. It's not too often that they have to go top up, but that is still done on regular supply missions, that they add water, they add oxygen, or I believe they just split water into oxygen, if I'm not mistaken, but I'd have to double check that. And applicable for underwater, like theoretically, absolutely yes. And this is how like nuclear submarines work. They'll have like oxygen candles where they burn, well, at least in the old days, they like would burn a substance that gives off breathable oxygen, and they'd have a full like functioning life support system. But in diving, if you're going that deep and going that hard, you're going to just do commercial diving where your gas is supplied from the surface. You don't have to have an actual underwater base. Quick thing though, I actually dove. There's an underwater like research place in the Florida Keys that I got to go dive. And we do some research there. I led a kids summer camp to go look underwater. They have a little functioning underwater base that they can sleep in, spend the night in, and stuff like that. So it does exist. It's just very niche.
Hello. So, like you mentioned that nowadays you have a dive computer that monitors all the sensors, monitors your gases, etc. But the computer is like, or the computer as we know it is like a fairly recent kind of thing. So back before the age of modern computers, how did they did they do any of this sort of what kinds of diving did they do? And when they did do it, how did they, did they just turn the knobs manually and pray that it was about right?
That's a good question. Yeah, there was a Wild West period when early Navy divers were just going down and diving stuff and then coming up with symptoms. So the foundational decompression theory was just figured out by which divers got symptoms and which ones didn't, and it was just trial and error to figure out how we get them back up safely. It's developed a lot since then, but in the early days, that's how it worked. And computers are relatively new. When I was becoming a PADI dive master, I was doing some assistant instructing work, and we were still teaching with the tables. So we were still teaching students how to sit down, pencil and paper, write out, plan each dive here, which gets really complicated. I can't do it fully out here, but you go to a depth, you spend a time there, you go to a pressure group, and it's easy for one dive, but then when you need to go decompress, you slowly move back out of pressure groups and add that to the next dive. And yeah, that can get pretty complicated pretty quickly, but it's totally doable by hand.
Do you know if they were doing so? I would imagine that's totally viable for your 40-meter sort of quote unquote normal dives. Do you know when all of these sort of more exotic gas mixtures started entering the picture?
Oh, that is a good question. I don't know when that started, when they started experimenting. It was definitely the Navy at some point. Early on, they were doing a lot of sabotage type of stuff and doing some crazy shit. So I don't know when that all came in. Sorry, what was the other part to that question?
No, that was mostly it.
Okay. Unfortunate. Oop.
Thank you.
Hi. So you mentioned that computers are relatively new in diving. Are there any other advancements that are either new or on the horizon? Anything the way the field is changing greatly?
That is a good question. I'd say in the realm of actual barophysics that we've talked about today, not so much. It's pretty well understood. There are some refinements going on for different algorithms used in decompression theory. The compartments I talked about are just one of many possible models to use, and this is the most common, but there's a lot of different ways to model this. As we've come to understand that silent bubbles are in our system, where is that? As we started to understand this also changes how we model decompression occurring, because instead of it just decompressing through a solution, we now have to worry about how bubbles affect this calculation, stuff like that. So there's a lot of debates going on, though from what I could tell in my research, they're kind of just moving the fuzzy line back and forth, and it's a little different for every diver. The number of bubbles we see in a diver will change quite a bit on the same diver on the same type of dive, just on a different day. So I feel like we're kind of pushing the limits of what really makes sense for the algorithms in a lot of cases.
Yeah, thank you.
So earlier we were talking about the ratio to of saturation divers. That was 10%, right? I'm aware there's also exosuits where people enter these big thick metal juggernaut type suits and they have these little metal pincers, and basically they're at 1 atmosphere the whole time, even when they go all the way down. Do you know how many dives are done with those exosuits compared to the ROVs?
I think they're extremely rare. I didn't really see much on the topic, and this was a little bit outside the scope of like a body under pressure, so I didn't get into that type of stuff. But it is, from what I've ever seen before, it's pretty much just for like research and a little bit of work, but it's so exceedingly rare because they're so difficult to manipulate. It's about the same as if you were in a little submersible or you were in like an ROV control or something like that. I'm not sure they're really practical.
All right, cool. Thank you.
Apple, are there YouTube questions? Do we have someone watching YouTube for questions? Okay. No real questions. Okay.
Oh, you're muted.
Sorry, thanks.
Okay.
I would have a question about what was the amazing dive you had, also the best experience. And I can say you that the tables I still teach today. Also, I had to learn it too.
Yes,
Let's go.
I think it's good to learn, but nobody's ever going to use those tables. But oh man, it's so hard to pick because my dives are so different. But if I have to pick one favorite dive, it's going to be wreck diving. I got to do a trip to the South Pacific, specifically Truk Lagoon in Micronesia. It was sort of like the Japanese effect of Pearl Harbor, where there's like 30 or 40 diveable World War II historic wrecks, and you can dive down, you can see like the firefighting equipment still on the decks, like you can watch the videos of the battles and of a ship getting torpedoed or something, and then go dive and come up the side of a ship where just this gaping like 40-foot hole just blows through like 6 stories of a ship before you, and it's just like incredibly breathtaking. It is absolutely a grave site, a memorial site, and just the sheer like awe-inspiring power of that and the impact of that has been one of the most incredible experiences of my life.
Thanks.
Do you know anything about like diving for like offshore wind? I'm a little bit curious whether there's been like an uptick in that sort of particular realm as a result, like as that's technology has become better and more powerful and so on.
I don't know for sure, but I would really bet to say that no, they're not really using commercial diving for that. Because they're placing out so many of those, I'm sure it would be just such a hassle to like get divers set up, go up and down. And we've gotten so good at drilling for oil under the ocean that they leverage a lot of the same hardware and techniques to drill in a foundation and stick that pole in. Anybody else?
That's it for.
Okay.
Excellent. If there are no further questions, I'd like to say a huge thank you to Mako Foxǃ for their lecture on surviving extreme pressure and barophysiology. We will be moving to another post-lecture world here in a few minutes. Thank you again to Mako as well as our YouTube attendees. Have a great Saturday, everyone.
Clap, 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 clap.
Clap, 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 clap.
Yay.
Too early on the clap.
Yay.
We're too early.
That was good stuff.
Oh, man.